acetal formation. So the general reaction that we're looking at here is the reaction of a carbonyl. So R prime equals alkyl, aryl, typical organic fragments, or H. So this is both for ketones and for aldehydes. If it's made from an aldehyde, it used to be called an acetal. If it was made from a ketone, it used to be called a ketal. Acetal is taken as the general name for all of these now. So this reacts with, we'll call this double prime alcohol. And we need two of these. Okay? This is a reversible process. Okay? So we have to shift the equilibrium that we're engaged in, and it's done with an acid catalyst. So we have catalytic acid. Hydrochloric acid can be used, sulfuric acid, those are the typical laboratory reagents that are readily available. So then what is formed here, so there's the fragment that came from my ketone or my carbonyl compound. I'm going to switch to red here for the parts that came from the alcohol, OR double prime and OR double prime. So there are some key things to note here. What we have now effectively, if we just look at this, this is an ether linkage, carbon, oxygen, carbon. And the same on this side, we have two ethers at the same carbon. And this is an acetal. Okay, that's the acetal functional group. Now, what I want you to notice is that we went from a carbonyl that's partially positive and reactive to nucleophiles to ether linkages. And we know that ether linkages are stable to strong bases and to reaction with strong nucleophiles. So this is actually going to be a way that we can protect aldehydes and ketones and keep them from undergoing reactions. Remember the concept of functional group or interconversion, where we turn it into something that's not reactive, and that's called a protecting group. And so we'll find that these are useful protecting groups. Now, I said this was an equilibrium, so where's the rest of it? Well, the oxygen here is still present, and it's now bonded to those hydrogens that came from the alcohol. So I've used the colors to coordinate things here. Of course, we've still got a lone pair here. And what we do is we use techniques to remove water when we're trying to form the acetal. One of them is to distill it off. And if we do that, we use an apparatus called a Dean-Stark. Not aware of that having any relationship to Starkville condenser, which allows us to evaporate or boil off the water. Usually it's actually an azeotrope, and then the Dean-Stark condenser allows the azeotrope to separate, and we can remove the water. Or you can add agents that bind the water in lab, perhaps. You've used magnesium sulfate, and so you can just throw magnesium sulfate in the reaction. The water binds physically to the insoluble solid that removes it from solution and, of course, from the equilibrium. You remember that principle from Gen Chem? We change equilibrium. Le Chatelier's principle. We remove the water, we shift the equilibrium. Okay, so that's the general reaction and the features, but let's look at some specific examples. So, not benzene, I want a carbonyl here. So let's just take cyclohexanone. We can react it with hydrochloric acid in methanol, and we can form the dimethyl acetal. And you see we have those two ether linkages on the compound. So that's very straightforward. But one of the best and most useful alcohols is to recognize that we don't have to have the alcohol in two different molecules. And so we very widely used is this alcohol. Anybody know what that one's called? Ethylene for the two-carbon fragment, and the diol, it's ethylene glycol. That's the antifreeze in the cooling system in your car. Now, it doesn't get nearly as cold here as it does, for instance, up north, where this is much more critical. But we do get a few cold days here where you may want to make sure you have some ethylene glycol in your radiator and in the cooling system so that it doesn't freeze and rupture the block of your engine. So with the alcohol being a diol and the two alcohols in the same molecule, then we get something that looks a little different. Don't want you to be fooled by that. And here's the fragment from the ethylene glycol. So we get a 5-membered ring formation. This actually makes it more stable, and that's part of why this is such a useful protecting group. So that's more common than, for instance, the dimethyl acetal. If we're going to try and do a protecting group, typically we'll use this ethylene glycol. I want you to remember this because there are 6-membered versions, there are sulfur versions, and all sorts of these that make their way into different parts of the chemistry. All right, now how does this occur? So the mechanism here picks up on what we learned about water, right? Remember, the difference between an alcohol and water is the conversion of one of those protons into an organic fragment. So I'm just going to take the simplest of reactants here, acetone plus, and for simplicity I'm going to illustrate methanol like this so that I don't spend a lot of time drawing in methyl groups and things. We're going to react that with HCl, and this will produce that dimethyl acetal. It's not really a smiley face, but I thought it might be fun to look at today. It popped out at me. So anyway, let me erase that part and we'll go back to studying the chemistry now. Anyway, I guess that works better when there's a live audience and they laugh for you. Suppose that's why television programs use canned laughter. All right, so here's our reaction. And when we write mechanisms, and this is important, I think, as you begin to learn and to solve mechanisms on your own, you need to write the reaction. So we write out that reaction because we want to always keep in mind and in front of us what the actual product is. Because if we draw a mechanism and we get the wrong product, that's going to obviously be the wrong mechanism. Hence my rule of thumb, the correct mechanism always produces the observed product. Seems obvious, but I can't tell you how many times I see those kinds of mistakes. All right, so we have an acid, we have a carbonyl, and again, our productive steps here are this reacts to get protonated in an acid-base reaction. Remember our reversibility principles. We make the protonated carbonyl. Okay, we're writing out sort of the full mechanism now, so I'm going to try and keep up with my chloride as I go all the way through. That has now greatly enhanced the electrophilicity of this, and so here's now our electrophile. Where's the nucleophile? Nucleophile is this alcohol. So that alcohol acts as a nucleophile. It attacks the carbonyl. That pi bond swings up to become a lone pair. Again, this is reversible also. All right, now we have here a protonated alcohol or protonated ether, and we see that's where our alcohol came in. We've got to move that proton around. It's important that you not draw this as a 4-membered ring transition state. Now, I just dealt with in the last section a 5-membered ring intramolecular transition state. Those are accessible under normal conditions. But this, remember, this is actually going to be in a methanol solution. There's water in there. There's all this methanol. And so these things are going to be hydrogen bonded to a shell of methanols. Of course, the oxygen close to this one. And in this case, it'll be the hydrogens that are hydrogen bonded here, and the oxygens from methanol will be hydrogen bonded there. And there's this huge complicated network of this. So it's not an intramolecular 1, 2, 3, 4 proton transfer. And that's one of the key things I try to communicate to students. This is very important for you when you go on to biology. People will often draw these mechanisms. I'm not blaming the biologist per se, don't misunderstand me, but what you'll see in biology textbooks or even in chemists who are trying to take shortcuts, and I think this is a key miscommunication that I want you to walk out of my classroom understanding clearly, because these kinds of compounds are very important in biology. So let me redraw this now that we've discussed this hydration shell that's around it. And so it really is a system where we've got all of these dynamic things going on. There's the chloride to balance the charge. And it's going to be, remember, these molecules are not stable. They're vibrating. They're moving all around. And it's going to be this bond getting longer and something hydrogen bonded over here. But we're going to illustrate it because I don't want you to think that it's this intramolecular thing. I want you to communicate. Remember, despite popular misconceptions, I can't really read minds. I can read what you write on the page or the selection that you make in an exam. So what I clearly want you to show is that you understand this is not a 4-membered ring transition state. You can use chloride. There might be an alcohol out here. Any of these could act as the base to pluck off that proton and in equilibrium produce something that we haven't seen before. Now, this can be the way I just drew it. That would be a protonated alcohol, hydrochloric acid. I'm not really worried about those details. I just want you to learn how to communicate that you know it's not a 4-membered ring transition state here. Now, let's look at this compound. This is a new functional group that we haven't seen before. It's called a hemiacetal. Okay, a hemiacetal. Hemi from hemisphere, remember that's half the earth. We live in the northern hemisphere, there's the southern hemisphere. And so if we look at this, we see that we have 1 carbon-oxygen-carbon linkage. That's an ether, like we saw for our acetals, right? There are 2 ether linkages. So we have an ether, and then this is an alcohol. So we're kind of halfway to the acetal, and so we have half an acetal, it's a hemiacetal. These are really important in biomolecules, particularly in carbohydrates. They're very prevalent in carbohydrate chemistry and the linkages where we put strings of simple carbohydrates together like glucose to make sucrose, and then bigger things like starches and cellulose and so forth, and these linkages are very important. So this is, again, a very critical concept for you to understand, and typically we're going to see these in aqueous environments in biology, so that's important that you understand this hydration issue. All right, so we're halfway there. We've plucked the proton off of the alcohol and the ether linkage. Now we have to protonate the other side. So this alcohol has 2 lone pairs. We can bring in, and I'm just going to use HCl again. We protonate. That alcohol side. Now again, remember these are all reversible reactions, and depending on the exact details of the structure, like what substituents are on here, you get different proportions of all of these intermediates in a reaction. There's my ether linkage. I now have a protonated alcohol here. Let's get the charges. First the atoms, and then the charges to balance things. Now, again, what you note is we've converted a hydroxyl group, which is a poor leaving group, into a protonated alcohol, which contains a water molecule, a good leaving group. And so we now have an intramolecular nucleophile electrophile reaction. That's the way I like to characterize it. This lone pair from the ether oxygen can come down. Of course, that carbon can't have more than 8 electrons. So that carbon-oxygen bond has to break. Again, this is a reversible reaction. And we have created a new oxonium ion. Remember this, and I'm going to put this in explicitly here. That's a methyl group from our alcohol that we started with, methanol. Now, you don't want to drink methanol. Alcohols are very prevalent right now. Ethanol and isopropanol and hand sanitizers and things. Don't ever use methanol. Methanol is what's called wood alcohol. If you ingest it, it will destroy your optic nerve and you will become permanently blinded. So recently there have been several recalls of hand sanitizer by the EPA because of the presence of methanol in those materials. So make sure you don't have methanol in there. Now, here's our water molecule. Remember we said we were going to lose a water molecule? There it is. And that's the water molecule that we need to remove to shift the equilibrium that we can do with a solid drying agent or with a Dean Stark condenser. Okay, so we've now got a new electrophile. And do you see the relationship between this methylated oxonium ion and the protonated oxonium ion we had up here? Those are both really good electrophiles. And so, of course, water can re-add, and we just go back here. But if we have a methanol molecule attack instead, we get, again, in an equilibrium process, there's our chloride to balance out our charge. And now we're very close, you see. What do we need to do to get from this intermediate to our acetal? What I hope you can notice pretty quickly is we need to lose a proton. So we use a conjugate base, chloride, methanol, water, whatever's close by, it doesn't matter. That will get us to the acetal product. So there's the mechanism of acetal formation. We're taking now and combining many of the ideas that we've learned from hydration and other chemistry.